Hello guys, welcome once more to our YouTube channel. Today we are looking at Northwest Mock 2023 physics. We are continuing our revision process and we hope that you enjoy some physics before going into rock physics on Thursday. Let's go. Okay, so again, you know what you do, right? So you just pause this video, read through the problem, attempt it. If you cannot, check out what we've done. Let's go. So state two ways a capacitor is similar to a semiconductor diode. All right, so let's look at them. Well, semiconductor diodes have a depletion layer that separates the p-type region from the n-type region, as a capacitor have a dielectric between their blades which separates the positive plate from the negative plate. That's a very good similarity there, right? Good. Now, when reverse bias, a semiconductor diode blocks DC current like a capacitor. Yeah, capacitors, they block DC current. Why? Because the material between their plates is a terrible conductor of electricity. Okay, so the dielectric material is not a conductor of electricity. Sometimes you hear about air, you hear about wool, right? Good. So now let's look at B. B says a fine layer of silver is deposited on each side of a sheet of mica, which is 2.4 centimeters squared. That's area, right? In area, to form a capacitor of capacitance 1.2 microfarad. If the dielectric constant of mica is 6.0, calculate the thickness of the mica sheet. Okay, let's do some little work here. Capacitance is basically what? E of the medium, right? Permittivity of the medium multiplied by area of cross section divided by separation of the plates, D. So the permittivity of the medium is basically relative permittivity multiplied by permittivity of free space. And they've given you relative permittivity here. That's what they call the dielectric constant of mica. That's just the relative permittivity of mica, okay? So that's 6. So we can put it here, multiply by the dielectric of air, cross-sectional area divided by D. But now I'm looking for D, right? Because we're talking about calculating the thickness of the mica sheet. So that's the separation. How thick the mica sheet is will determine the separation of the plates. So make D the subject, so we have this, right? So we can get over here and then substitute E0 here, or the relative permittivity ER is 6, E0 is 8.85 times 10 to the negative 12. Area of cross-section is 2.4 centimeters squared, which is 2.4 times 10 to the negative 4, because you have to convert the centimeter squared to meter squared, divided by C. And our C here is the capacitance of the capacitor, which is 1.2 times 10 to the negative 6 farads. So if we simplify that, of course, our D is 1.1 times 10 to the negative 8 meters. Okay, so we're done with that part. Let's go to the next. The insulation of the mica breaks down when subjected to an electric field strength of this. And it is desirable in practice never to exceed half of this strength. Calculate the maximum allowed working voltage. Okay, so our field strength there is 4.5 times 10 to the power 7 volt per meter. Now remember that I was given to you as in volt per centimeter, so convert centimeter to meter. You basically have to multiply or divide since it's centimeters already down, so you have times 10 to the negative 2 there, which would come up, and then you're multiplying by 10 to the negative 10 to the power 2, so that gives you 10 to the power 7 here. So our E0 will be half of this. So when you have this, you have 2.25 times the power 7, right? Volt per meter. So that is what is desirable in practice, okay? That you don't exceed half of this strength. So this is what we need to use in practice. So our E0 is basically field strength is peak voltage divided by separation of the plate. So, well, you notice that our V0 there would basically be E0 multiplied by D. And so our E0, maximum possible electric field strength, is 2.25 times 10 to the 7, multiplied by our D, and our D is 1.1 times 10 to the negative 8. So maximum working voltage is 0.25 volts. All right, guys. I hope you like the problem. I hope you enjoy this part of capacitors, right? Using, you know, permittivity and relative permittivity, which is also known as just the dielectric constant of the material. All right, wish you all the best, guys.